Well, good evening, ladies and gentlemen, and welcome to the 2016 Eugene Shoemaker Memorial Lecture. You're going to hear a little bit from our speaker about Gene Shoemaker, and so I won't dwell on that. So I'm Paul Davies, I'm director of the Beyond Center, and this is one of our annual lectures. The next one you saw being advertised on the preceding slide, so take note and try to come. But my main task today is to introduce today's speaker to you. So he started his career at that little place down the road called the University of Arizona, where he did a PhD in astronomy. He went on to become Brigadier General in the Air Force. And then he became head director, I guess, of NASA, the NASA Ames Research Center, which anybody who knows anything about NASA's project on the origin of life and searching for life elsewhere, the subject of astrobiology, will be aware that that is the leading institution. But about 18 months ago, he took up an extraordinary challenge to deal with the Breakthrough Initiatives, and he's, let me see if I can get this right, he's chairman of the Breakthrough Prize Foundation and executive director of the foundation's Breakthrough Initiatives. As you will hear, these are initiatives created by the extraordinary vision and dreams of the philanthropist Yuri Milner, but the person who is charged with the task of turning the dreams into reality is our speaker tonight. So without further ado, I will introduce you to Pete Worden, who will tell us all about the Breakthrough Initiatives. Thank you, Pete.
Well, thank you, Paul. I'm really honored to be here, and particularly honored to be giving the Gene Shoemaker lecture. I met Gene in the 1980s, which is a long time ago. And I was, as noted, I was an Air Force guy, and so he gave me a little bit of a hard time. But I eventually became the head of technology in the Star Wars program, and we had a kind of a scam. It was actually a lot of scams, but we wanted to test space weapons. And there was this thing called the ABM Treaty, and it said you couldn't test space weapons in Earth orbit, if you read it. So we decided we'd test them in lunar orbit. And so we had a mission called Clementine, and that we sent a space weapon to the moon, and then we were going to go off and go to an asteroid. And but we thought we needed some scientific cover for this, and and there was really cool science it was going to do. So Gene agreed to chair our science advisory board and make sure we did real science. And it was a really cool mission. It went to the moon. It mapped the entire moon. It was our first mission to the moon in 20 years. It used the technical term, it crapped out on the way to the asteroid. But Gene was really kept us on the straight and narrow to do really cool science. So I'm very proud of my association with him, and the world lost a really great scientist when we lost him. So it is truly a great honor for me to be here and giving a lecture in his name. Okay, it's dangerous to give a military guy a laser weapon, so. But as noted, I'm the executive director of the Breakthrough Initiatives. I'll give you a little bit of background. Yuri Milner is a Russian physicist, and at the end of the Cold War, he decided that capitalism was cool, and he went to Wharton, got an MBA, and founded some of the first big investment groups. But he started working heavily in Silicon Valley, where he now lives. But one of the things about 6-7 years ago, he was looking at list of who's the most admired people on the planet. And there's these are compiled by various groups. And he was really dismayed to find there are very few scientists on these lists. I mean, you might find Stephen Hawking's name or a few others. So he decided we should do something about it, and he initiated the Breakthrough Prizes, which are the largest prizes in science, about $3 million, 3 times the size of there's some small prize in Scandinavia, I think I've heard of. But he persuaded other high net worth people like Mark Zuckerberg, you might have heard of him, Sergey Brin, the co-founder of Google, and Wojcicki, the founder of 23andMe, and Jack Ma, the founder of Alibaba. So we give out 7 $3 million prizes every year. We have some New Horizons prizes or early career prizes of $100,000. And one thing I'd really like to encourage, if anybody knows a high school student, we started last year with a Junior Breakthrough Prize, which is to do a 10-minute video on some science principle. The young man that won it was from Ohio last year. Really cool. He's starting his freshman year at Harvard this year with a $250,000 scholarship from us. So I don't think he could have gone there without scholarship. But the school got a $100,000 lab, and maybe the coolest thing was the teacher that he thought inspired him got a $50,000 check. He didn't tell the teacher he'd nominated him. And when we called up, the teacher said, "Is this a call from Nigeria? You want my bank account for what?" So anyway, it's a pretty cool thing. It's the prize is open now, so look on our website. But part of the prize was to have a ceremony, and we made an agreement with the Vanity Fair, who does the Oscar party, and so they decided to really do it upright. And it's the only black tie affair in Silicon Valley, but they decided to have it on the campus of NASA Ames Research Center. And since I was the landlord, I got invited. It's always good to invite the landlord. But I got to know Mr. Milner and the rest of the folks. And a couple of years ago, Yuri talked to me about his dream of really focusing, doing science about life in the universe. So I'm going to tell you about a couple of our initiatives today, and which I think are really cool. It didn't take much persuasion to get me to leave NASA, even though it was the job I loved most in my career, to go work on this. The first initiative was a little over a year ago. It was July 20th, 2015. We called Breakthrough Listen. This is about a renewed search for extraterrestrial intelligence. We made the announcement in London at the Royal Society. There's Yuri there, and you probably recognize the other guy, who has generously been one of our key advisors and has played a huge role in our thinking about life in the universe. And I thought his quote at that conference or at that announcement was really cool. I mean, a lot of people say, "Well, why are you doing this stuff?" And I think you don't need to get any further the justification that, we need to know, are we alone? Just kind of way of background, this is an old question. One of the more interesting parts of this was in the 1950s, Enrico Fermi, the famous nuclear physicist, kind of posed a dilemma. He said, there's nothing really unique about our planet. In fact, the more we find out about it, it's, there's a lot of planets that might be like the Earth in the galaxy. We're not a particularly old planet, not a particularly young one, roughly 4.5 billion years old, that there should, if life is everywhere, which we assume it is, that, and if you assume that life eventually will develop, more complex information systems and eventually develop intelligence, that, and eventually figure out how to go between stars, which, by the way, is the second part of our initiative, that these aliens should have been sort of spread across the galaxy, and so where are they? This is a really fundamental question, and there's a lot of answers to it, but one of them is we may be the first. Another one is maybe they're already here, and in fact, when I was the director at NASA Ames, I was convinced half my staff were aliens anyhow. And anybody who works with NASA knows that. But other than them, we haven't seen any other evidence of aliens. This is a really old question. The first, I think, probably serious technological discussion was by some of the greats of the era of electricity and radio, Edison, Marconi, and Tesla. And they pointed out that radio could easily be used to communicate between planets and maybe much more distant. In fact, I think it was Marconi that persuaded the U.S. Navy in 1924 that, that was when Mars did one of its closest approaches to Earth, that that'd be a good time to look for Martian radio signals. So the Navy took that seriously and ordered at least all the government radios to shut down during the few hours of closest approach, because that might be when we could most likely hear radio signals. Needless to say, we didn't hear anything. And of course, after that, the Navy went into more goofy stuff. And it really, there wasn't a lot of scientific investigation on this topic for a good many decades. But that all changed with this gentleman, who's Frank Drake, who, by the way, is a co-chairman of one of our advisory panels. And he pointed out that the new science of radio astronomy offered some real potential. So in 1960, he, along with a young graduate student, Carl Sagan, started looking for alien signals using the National Radio Astronomy Observatory. I asked him, did you ever find it? And he said, well, actually, the first time they turned it on, they did. They turned it at the nearby kind of solar-type stars, Tau Ceti and Epsilon Eridani, and they got signals from both. Although I think they later decoded them and said they were "I Love Lucy" or something. So, doubting that the aliens would broadcast those, it moved on. Now, Frank, after a lot of his work, along with others, came up with this famous equation, although it's not really an equation because all the terms are multiplicative, but that is often used to figure out, how many, how many possible civilizations that you have in the galaxy. And I don't want to go into a lot of detail other than saying that NASA and other space agencies around the world are beginning to march down this equation and actually give us real numbers. We now know that this number is essentially 100%. Virtually all stars have planets. We know that the number of planets in the habitable zone is roughly a quarter. Now these are kind of unknown things, but potentially we can find something out of those by scientific study. Now there have been at least reported detections. The most recent one was about a month ago by a Russian radio telescope, which the Russian government quickly said was no, it was a secret Russian spy satellite. So I don't know, you can believe them or not. We did look at that star with some of our equipment and didn't find anything. But one of the most famous discoveries was in the mid-'70s. Then is now, a lot of the work being done was not being paid for, and a lot of volunteers. The gentleman in the center here was a volunteer at Ohio State University that had the Big Ear radio telescope, which just shows the, really cool radio telescope. But it shows where it happens to a lot of science. There's now a golf course there, unfortunately. But I think it was 1977, Jerry identified this signal, which looked kind of what you might find, and he wrote "wow" on it. So this is the famous "wow" signal. It was only 30 seconds and never seen again. We looked at that spot repeatedly. But there are a fair number of transient kind of signals, and really there hasn't been much way to follow up on them. In fact, about 2 years ago, we started looking at the work that was done, and we found, we really haven't done very much, even in the radio spectrum. We've only looked at a few frequencies, and we haven't looked at a lot of the sky, and this is sort of a plot of what had been done prior to our program. So Mr. Milner and his advisors, including myself, said, this is a good time to really do something more comprehensive. Now I put this scientist up. This is Jill Tarter. She's dedicated her career to looking for SETI signals. You see behind her the Allen Telescope Array, which was the last major effort, which was done about 10, 15 years ago by Microsoft co-founder Paul Allen. So there's been a fair history of high net worth people trying to push this. Well, Jill said, you know, what we've done to date is sort of, if I wanted to look for fish in the ocean, if I went and took a glass and dipped it into the ocean and said, look, there's no fish, and then gave up, that's kind of what a lot of people have done. She said, at least we ought to have a trawler. So that's what we've decided to do with Breakthrough Listen. We were able to assemble a team here. This is the initial team. We contracted with the University of California at Berkeley to lead this effort. We have an advisory panel that Professor Davies is a member of that is about 25, 30 people, chaired by the former head of the Royal Society, Lord Martin Rees. So we've got some people that really know what they're doing. But what we've decided to do is we've leased 20% of the time on this radio telescope. This is the Green Bank telescope, 100-meter steered antenna. So that's the size of a football field in it. It's kind of a pretty cool instrument. It's the largest steered antenna in the world. We also have added, are adding here this month, the Parkes radio telescope. It's a 65-meter radio telescope in Australia, so we can look at the southern sky. It's the second largest steered antenna in the southern hemisphere. So these two antennas are going to do a pretty broad search. But we also recognize that there are optical signals, that increasingly we are communicating with optical frequencies. So we've begun an optical SETI program at the Lick Observatory. It's not the telescope with the laser coming out of it. That's the 120-inch, but the sort of white round dome immediately to your left. There's two of them there, but it's the one that has the paint still on it. Is the automated planet finder, a 2.5-meter telescope, and we've been using that to look for optical signals. This is the 500-meter telescope that is just, in fact, I think it's dedicated next week in China. We've been in discussions with them. This will be the world's largest radio telescope. They've already agreed to do some SETI signals, and so we hope to be working with them. The next really big instrument is the Square Kilometer Array in South Africa. We are in discussions about a rather major program involving the Square Kilometer Array. When it's finished, it will have a total radio gathering power of a square kilometer radio telescope. The first element of that, the Meerkat radio telescope, is being completed at the end of this year. One day of even our current observations, even without those two new telescopes, is equivalent to a year of previous searches. We're going to look at 1 million stars. This is out to about 1,000 light years. This kind of is the maximum range where we think that if somebody was watching the Earth, they'd begin to see industrial signals. You know, in fact, the first industrial signal was, I'm told by experts, was when the Romans cut down all the forest in Spain to smelt silver and change the atmosphere. So this is an interesting number. Of course, the majority of stars in our galaxy are concentrated towards the center of the galaxy, so we're going to do a lot of scans of the center of the galaxy, and most of the rest are in the plane of the Milky Way. So we're planning some pretty comprehensive surveys there. And for those of you that are really kind of into the geekiness of SETI, there's possible that other galaxies could have civilizations that solve the Fermi paradox, and there's a civilization that goes across the galaxy. Kardashev level 3 civilizations, for those of you that are familiar with that. So we're going to look at the 100 nearest galaxies for signals. Also, we are committed to making as much of the data as possible available. You can go to our website and already download some data. We also are supporting SETI at home, which is where you can download a screensaver. It's either download our screensaver or download something from the NSA. Ours is better. The net computing power of the several million screensavers is about comparable to the NSA's biggest computer, so we can do pretty well on that. How many of you have downloaded the screensaver? I'd encourage all of you to. We need your computer power. You know, this is a really cool program. But the fundamental question that Yuri and others ask is, what if, and by the way, we're about to look at, start some other programs to see if there's any life around the nearby stars. What if we found something, can we go visit? And so I will start with a short video here of our next initiative that introduces, this is Seth MacFarlane narrating this, who's been very helpful with this.
We are here. This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets and ventured to the edge of deep space. Where now?
So this is our next initiative, Breakthrough StarShot. We think now is the time that we can begin to think about interstellar travel, and I'll tell you a little bit about where we think we're going to go. This initiative was announced on the 12th of April in New York. Professor Hawking was there, and you can see sort of the team up there. In addition to Hawking, Mark Zuckerberg's agreed to serve on our oversight board. This, by the way, was the 55th anniversary of the first human in space, Yuri Gagarin, who I might mention Yuri Milner was named after. I've confirmed that with his mother, so it's true. But the objective here is to begin a quest that we can send robotic probes to the nearest star system, and I'll talk a little bit about what we're trying to do there. This, we think, is the next great leap for mankind. As I noted, I think the first one was Yuri Gagarin's flight in 1961. Of course, 1969, landing on the moon was the next one. The robotic probes have taken us, as noted in the movie, to the edge of the solar system. Voyager is about 130 astronomical units, so the astronomical units, the distance between the Earth and the Sun, out from the Sun. The nearest star is about 300,000 astronomical units, so at the speed we're going with that, we'll get, if we were aimed in the right direction, we'd get there in about 80,000 years, so probably not not something that you want to hold your breath for. So we need to figure out how to go faster. Now, I'm not going to go in a lot of detail here, but I work for NASA, which does a lot of cool things in the solar system, but frankly, I got to say, our solar system is so boring. So this is what I think is humanity's next set of interesting targets. These are the nearby stars. There are roughly 50 within about 10, 15 light years that are potentially reachable if you can go at some fraction of the speed of light. We chose 20% as our target. In fact, we now, as I said, noted that most stars have planets. Indeed, the instrument that sort of did the most for this recently was the Kepler mission, which I was really honored when I was the director at NASA Ames to have oversight for, which, and again, I won't go into all the details here, but essentially 100% of the stars have some sort of planetary system. There are probably an order of magnitude more planets than there are stars in the galaxy. But this is our target. This is the Alpha Centauri system. Those of you who've been in the southern hemisphere, it's the, I think it's the brightest star in the southern hemisphere. It's actually a triple star system. The primary star you can see with your naked eye is two more or less solar type stars orbiting with about a 70-year period around each other. And the third star is called a small red dwarf, Proxima Centauri. The stars, again, is that, compared to the sun, Alpha Centauri A is a little bit bigger, and Alpha Centauri C is or B is a little smaller, and then Proxima Centauri is much smaller. Now, when we made our announcement, people said, how do you know there's someplace interesting to go? And about 3 weeks ago at the European Southern Observatory, it was announced that the astronomers there had discovered a possibly Earth-type planet. It's about the mass of the Earth, more or less, orbiting Proxima Centauri in the habitable zone, which is defined as where liquid water could exist on the surface. So this sort of proved it's sometimes better to be lucky than good. So we've now, they invited me over to the press conference, so I said, yes, we got someplace to go. But there's a real reason that we're going there. Now, how many of you know what this is? Good. There's more of you. Put your hands up. That's it. These two Pokemon aren't found on Earth. We think we know where they are. So that's a good reason to go there. But this is hard. I mean, to kind of, I think most people know what this is, but to kind of give you the scale we're talking about is that if the moon was kind of where that screen is, and where you're sitting, Alpha Centauri is about the distance where the moon is, really. So it's, several hundred times further, 100,000 times further away than the planet. So it's a challenge. In order to get there in some sort of human scale, which we've picked at 20, 25 years, we need to go 1,000 times faster than we can go today. And this is a challenge. However, we note that, the 100 years before our space program began, we increased the speed 1,000 times. So we think that and I'll tell you why we think we can do it in the next, half century or so, or maybe sooner. But this is the challenge of getting things at a lot faster. Now, you could use rocket fuel. We did a calculation, and you could go to the nearest star with rockets. The mass of the fuel would be about the mass of the galaxy, so it's probably not quite feasible. We could use nuclear power. This will work, and there have been a lot of people, and there are still people working on things of fusion propulsion and fission propulsion, except that when we looked in detail on this, what they say about fusion power, it's the energy the future always has been and always will be. But I won't poo-poo this too much. I mean, there's people working on it. If we find that fusion propulsion works in the next few decades, we'll shift to it. But what we decided to do is go back to a much older technology, where you don't carry your fuel with you. it comes from someplace else. So we're looking at light sails. And this is probably an old idea. I mean, we found this letter from Kepler to Galileo where he talks about heavenly winds, and we're not sure what he was talking about, but we'll claim it was light sails. Indeed, this is a concept that's been talked about for the last century, most completely by Robert Forward in the 1960s. About the same time Yuri Gagarin was launched, Robert Forward, a physicist at Hughes Aircraft, began to talk about light sails, where you use the pressure of light to push things in space. This has been proven. This is the Icarus probe that's the Japanese launched and showed that solar radiation pressure, light pressure, can be used to propel things. There's been a couple other experiments since then. Trouble is, sunlight is not strong enough to get us to the speeds we need to go. But there are two trends that we've looked at that look really promising. The first is, can we make satellites really small and lightweight? And microelectronics, and I'll tell you kind of where we think we are on that, is getting there. The second, can we make lasers really powerful? And I'll tell you why we think that we can do that as well. So the idea is to build a humongous laser. That's another technical term. It's about 1 kilometer square that would put out 50 to 100 gigawatts of power for a few minutes. And then that would push a really tiny spacecraft, which we call a star chip. And these things are, coming along that weighed less than a gram. In fact, I brought one with me. So that's a mock-up, but these components exist today to make a full spacecraft, and I'll talk a little bit about that more in a second. This is what a typical satellite looks today. We're not going to send that interstellar distances with any laser we can imagine. But in your Apple Watch, hopefully not the Galaxy phone you brought, there's a computer that's about the size of what we would talk about as a star chip. These things do exist today. Again, as I pointed out, we're probably building one of these in the next year or two. These components exist today to do all of the functions of a spacecraft, including communications, navigation, carrying instruments, and so forth. This is coming along quite nicely. Indeed, we can go through and find that you can put together a spacecraft for less than a gram. And this is probably the next big revolution in spacecraft. So the idea is to attach one of these star chips to a light sail, 4 or 5 meters in diameter, that you would then push this laser on. Now this is a challenge because this is 50 gigawatts of power that's going to hit something pretty small and accelerates it at about 50, 60,000 Gs for a few minutes to up to 20% light speed. Now we've had an advisory panel. I'll talk a little bit about them, but we think this is feasible in the next few decades, and this is one of our really big challenges. Of course, the other challenge is putting this laser array together in some affordable manner. We could probably do this today if we had several $1 trillion. So this is not something that even Zuckerberg can afford. Although, use your Facebook, maybe it'll help. But what we're finding very interestingly is that Moore's law for computers is beginning to show true for lasers, that the cost of lasers is going down in a kind of log linear fashion, and the power is going up. So when we extrapolate this, it looks like we could potentially construct a laser array that would have the necessary power for roughly what somewhere between the Large Hadron Collider at CERN and the International Space Station, kind of levels that are more in line with what the world might want to spend on these kind of things. We realize this is like hugely hard. On our website, we've listed at least 20 challenges. We need to solve these. I kind of think we're roughly at the place that Kip Thorne and his colleagues were, a few decades ago when they started the idea to look for gravitational waves. In fact, we understand Einstein, when he talked about the concept, somebody asked him if it would ever be possible to measure them. He said, absolutely not. So, but as you know, we did that. So we think this is a place to start. We have a distinguished advisory committee. We've added a few members in addition to these folks, a couple Nobel laureates and others that have had real expertise. As I said, they met for the first time a few weeks ago and concluded that, yeah, this is really hard, but it's a really cool thing to start with. So what we're doing over the next number of years, probably 5 or 6 years, Mr. Milner has committed $100 million to focus on the hardest two problems. One is the sail. That can we make the sail out of material that is possible? And by the way, we found there are some materials that can do this. We're about an order of magnitude too heavy, but it looks like the physics at least allows it. And second is can we build a ground-based laser, a kilometer square, that's affordable? And we're going to be working on that. This is will be a completely open effort. We're committed to having a truly global open effort. If we're successful, in about 5 or 6 years, we will start building a prototype, which we think will be roughly $500 million to $1 billion. That we also think can be privately funded, that within Silicon Valley, if not other places, that could send one of these star chips to maybe 1,000 kilometers a second, getting an order of magnitude and a half faster than we can get today, and laying the foundation for building within a couple decades the system that could send star chips to Alpha Centauri. Now that we think it would clearly be a global effort, public-private partnership. Let me kind of just narrate at least our rough concept of how this might work. So we have this array, and by the way, it wouldn't look like radio telescopes, the artists. We have a mothership that's in an elliptical orbit that has hundreds of these things. We're not going to launch just one. That then unfurl. The laser array is suitably aimed, and then you fire for 2 minutes, and you hit the light sail and accelerate it really fast. After 2 minutes, you're a few million kilometers away from the Earth, going at 0.2 C. And then we're in coast for 25 years or so. We change the angle so that we don't hit a lot of stuff. There is a lot of stuff in interstellar space. In fact, that's one of our other challenges. Then, again, we're sending hundreds, if not thousands of these to Alpha Centauri and now Proxima Centauri. Then after 25 years, they fly through the Alpha Centauri system in about 8 or 10 hours. The cameras on board will image the planet. Here you can see the images. They've already got the answers. And then another magic thing happens. We use the light sail as an optical element, and there's a small laser on board that fires the signal back. 4.5 years later, it comes back to Earth. We use the transmitting array as a receiver. This is a kilometer telescope. We calculate we can get a few kilobytes per second. So this seems to be feasible, but really hard. But it's kind of a cool thing to work on. I will stop there. I'll be happy to answer any questions, but I can't think of a more cool thing to do after I retired from the Air Force and NASA than try to build a star chip.
Thank you. So we do have time for questions, but before that, in honor of Gene Shoemaker and the speakers, each year we present a little trophy, which I shall show you here. And Gene made his reputation by pioneering the field of asteroid and comet impacts. And so it seems very fitting that we have attached to this little trophy here a piece of impactite. So that's sand from Libya, I think, somewhere in the Sahara, made by an impact with a meteorite some time ago. So let me pass that to you with our thanks.
Thank you.
I
have another little story about Gene. he knew I liked asteroids. In fact, by the way, the next 2 days in the Grand Duchy of Luxembourg, they're having a meeting about mining asteroids that I helped persuade them.
Right, yes.
And a few hundred million euros if you're interested in moving to Luxembourg. But my interest in asteroids went way back, and so some colleagues, along with Eugene, wanted to name an asteroid after me. And so they found one. And but then they went to the International Astronomical Union and said, you can't name it after him. And it turns out there's some obscure phrase in agreement that you can't name asteroids after political figures or military officers.
Right.
And so they named it after my wife.
Oh, that's very good. Yes.
She said, when I told her they did that, she said, yeah, that'll be the one that destroys the Earth.
I have no military impediment, so I have one named after me too. We didn't have to name it after Pauline, but she get the next one.
Anyhow, thank you.
And also, the other thing about Gene is that his ashes, or at least some of them, went to the moon. In fact, that's right. The only human so far buried on the moon. So an extraordinary individual. Anyway, we do have time for questions about all and any of the subject matter for this evening. Yes. Hello, and it's good to see you again. It's one of our regulars.
Well, those are really good questions. I think the answer is yes. We would probably have some precursor missions that would just go to interstellar space. There's a lot of stuff in interstellar space. In fact, it may be that that's the biggest challenge, is flying through it. But one of the interesting questions, I mean, there's the Oort cloud of objects. We would probably fly by Oort cloud objects earlier missions. The other thing that's kind of interesting, and there is postulated that there are brown dwarfs that are sort of, failed stars, and there may be a lot of them. In fact, I think I heard some statistical, there might be one within a light year. If we can find those, you may have a planet orbiting those that is in the habitable zone. So there's a lot of really interesting stuff. In fact, when we made our announcement, on the StarShot announcement, we had Freeman Dyson there, and he said, forget Alpha Centauri, just go to the stuff in between. So that's certainly an interesting question. The other question about doing more than imaging, and the answer is we'll look at that. And we have an annual conference called Breakthrough Discuss, and one of the key topics this year, will be in April, is what else would you carry on these star chips? Magnetic field measurements, maybe even be able to detect molecular signals that might indicate that there's a life-bearing planet. So this is a topic that we're really going to start looking at. But, if you're going to send a bunch of these things, and probably half of them will fail, we want to send more than just a camera. But good question.
Right. Yes, okay, you get the second one.
That would be horrible. We have on board the spacecraft, there's a computer, and there's also 4 small lasers that will orient it. So we would lock on the planet. Now, before we even go, we're going to be mapping the planetary orbits. We already know there's at least one planet at Proxima Centauri. We're going to be looking over the next few years to find planets in the Alpha Centauri A and B systems. So the idea is that you would use these lasers to kind of lock, and we wouldn't fly that close to the planet so that you wouldn't have to do a real fast spin. But obviously some of them will fail, and so that's why we're going to send a lot of them. Good question.
As a lady there.
Well,
so actually, I should be repeating these questions for the benefit of...
The question was, doesn't the laser destroy the chip? And that is one of our challenges, because you're putting this really powerful laser on this sail. There's 2 key things that we have to do so the laser that pushes it doesn't destroy it. The first thing is it has to have high reflectance. So in fact, you need to have that to push the sail and the attached chip. The other thing is that you have to have what doesn't get reflected, minimal gets absorbed in the sail. We think we have materials that can do that. The chip itself would have to have a really high reflectance coating on it, probably 4 nines, 5 nines to avoid being burned up. But that's the critical question. That can we put that much power on a small thing without burning up the material? But that's probably our number one challenge. Theoretically, yes, we can do it. In practice, it's going to take a while.
So let me move back and then come forward. So question over there. So
the question is how big the sail would be, and how do we make sure we point at it and it doesn't get off the direction. Those are two of the challenges. The sail itself is about 4 or 5 meters in diameter. The second question is how we keep things pointed. We have to keep it pointed within about an arc second, but optical systems typically can do that. The other challenge is that we've got to keep the sail so it doesn't, it doesn't get pushed out of the beam in those 2 minutes. There's a couple ways to do that. One is the shape of the sail. In fact, you'd like it to be a parabola as an optical element anyhow. That's a very good shape, so that you keep it in the center of the beam. The other thing is that the beam itself is such that it would push it towards the center. So there's more power in the edge than the center. So you have to construct the beam in the right manner. In theory, those are all doable. That's, like I said, the other challenge is building that laser beamer in such a way that it can do that. And that's why we're going to do lab tests and field tests in the next few years, and then we want to build a prototype, that's maybe 100 meters in diameter, 50 to 100 meters, and that can get these star chips to hundreds, maybe 1,000 kilometers a second. So, it's going to be hard, but fun.
I'll take the question in front here and then go to you there. Yes, gentleman here. Yes.
The question was about course corrections. Yes. As I said, there are these 4 small lasers that are orienting it, plus a larger signaling laser. The power comes from a radioisotope decay. Over the 20-odd years that it's in interstellar space, you can fire those to move slightly. We calculated that you might be able to get an astronomical unit or 2 course correction change over those 20 years, so it's not a big change, but it's enough that if we're slightly off, we can probably we can stay locked on the Alpha Centauri system. One of the challenges right now is we don't know where Alpha Centauri is accurately enough yet. So we're talking to some of the major observatories about getting more data. We know where it is in cross track, but not long track. So that's those are challenges. But yes, navigation is one of the other 20-odd challenges. But we do have some maneuver capability, not a lot.
Okay, it was a question that the gentleman in the white shirt there, and then Roger, you'll get the next one. Yeah.
The question is, how much power does the square kilometer laser need? It's about 1.5 gigawatt hours. That's a lot. But it's about what, say, a 200, 300 megawatt power plant puts out in a day. Our big challenge is to store the power. So we would have some sort of storage mechanism, batteries, or potentially flywheels, and you'd have to store the power from that's a mid-sized power plant. The most likely place for this beamer is in the Atacama Desert in Chile. When we figured that out, the Chilean government said it wants us to come and talk to them soon. So we're going to do that. They're positive, but that's a power plant that they actually have some of those that would be interesting. So it's a lot of power. It's really the storage more than the raw power.
Roger.
The question was how much deceleration in the interstellar gas density. It's a really small amount. It's less than 1% from the calculations we made. Bruce Drain at Princeton is our interstellar medium expert, and he's, but one of the big things we don't, I think you and I talked earlier today, we don't know a lot about the interstellar medium. Our biggest concern isn't the gas, it's the dust. And what the dust density is. The sail, it doesn't matter. I mean, you make holes in the sail, but it's really that chip, and we may distribute the chip with enough redundancy. I think we can shield it a little bit, but it really depends on the mass spectrum of the interstellar medium, and that's a big unknown. That's why I think we'll probably end up with precursor missions. As also we discussed, the density of larger things in the Oort cloud may be high. So these are challenges. Well, we need the sail as an optical element. That's a problem.
Okay, so there's a lot of hands. I'm somehow, because of the light in my eyes, not seeing anybody up there who might want to ask a question. Let me try to just favor going back a little bit. So there was a gentleman in the front row of the back section there. You sir, yes.
Yeah, the question is, what would we do with the data? What's the plan beyond? Of course, the fundamental question is this a life-bearing planet? And imagery will give us a lot of ability to figure that out. I mean, if the sort of home run is it's a life-bearing planet and has continents and things, and the real home run is you find factories and whatnot. Unlikely, but one of the key questions is, what do you mean by life-bearing? So there may be much different kinds of life, different chemistry. So one of our big challenges, and we've been talking to people here, is to have a series of seminars and conferences about what do you look for. And I think that our fundamental goal is science, but there's a broader goal, and there's really two of them. One of them is this is really a global effort. This is require the people of Earth working together. That has a huge value in really promoting science and a perspective beyond our solar system, really into the galaxy. The second longer term issue is there are a lot of people, that myself included, that are inspired by the idea of sending bigger probes, stopping, maybe even eventually sending humans, although I think probably by the time we get around to sending humans, there'll be something else that makes more sense, robotic kinds of systems. But this is, I think, for me and a lot of other people working on it, is the next big step for humanity in terms of space. There are clearly other things we need to do, but it should help also get people to work together. So we have a kind of twin objective.
Okay.
Yeah, there's a question right up here.
All right.
Yeah. Well, the question is, when do I think that humans will go interstellar, I guess. I don't know. I'd like to think that by the end of this century, that we'll have figured out ways that we can send humans or enough essence of what we are, interstellar distances. Some people that I talk to, I'd say a lot of the members of the advisory panel think never. But they do believe that sending a probe that begins that's part of us. Our objective is probably by the middle of this century to launch the first probes. I'm 66, so I want to be around when we launch them. I doubt if I'll be around when we get there, although there's a lot of people that believe the medicine's coming along fine. As long as I don't drink as much good wine, I'll be fine. But yes, that's the time scale.
I think we just had better limit it to 2 more questions. And so, a gentleman over there with the sort of stripy top.
Yeah.
Yes?
Well, the question is, how can it be financially sustainable? Our objective isn't to make money, but it's to focus the efforts of the world on a really awesome scientific objective. The early phases we think can be funded privately. Some of the world's great telescopes have been built, roughly $1 billion or so. So the first few phases that we want to do that privately. But ultimately, we're going to need to have governments involved. The big expensive element of this is the laser beamer, but it has a lot of other uses as well. If you can send a gram thing 20% light speed, you can send tens of kilograms at orders of magnitude faster than we can today. So this will enable if you have a Mars colony, getting payloads there in weeks rather than years. So it becomes a real advance in propulsion that will have a lot of other uses. So it's kind of there's reasons beyond going to interstellar distances that we think governments would build and maintain this.
Okay. The last question, perhaps I'll let you have the honor of picking
Why don't
the
way
question.
in the back? People
Yes,
never call in the
because
back.
they tend to be overlooked.
Yeah, back there in the striped shirt. The other. Yep. The question about the radio telescopes that we're using today, is the data available to the public? Now, we said we were going to make all of it available, and that's until we figured out what all of it means. It's a huge amount of data. So what we do is we take the data. We have correlators, which figure out whether there's a signal. Those signals are beginning to be made available on our website. It's through the University of California at Berkeley. We're going to work to make as much of the data that's practical available. We're also committed to, if we find any potential signals, of sharing those with everybody. In fact, next week there's the International Astronautical Congress is being held in Guadalajara, Mexico. There is long been a SETI working group that's part of the International Academy of Astronautics. The main question is how to make as much data possible. How do we characterize a signal as, is this something that is unlikely or is it maybe likely? One of the most interesting comments I heard about intelligent signals was about a month after we made our announcement, Neil deGrasse Tyson had an interview with Edward Snowden. I'm sure the NSA would like to know how he did that too. But he asked Snowden, this was about a month after we made our announcement, what he thought of searching for intelligent signals, and he said, well, you should assume that they're encrypted. Which is a good point. I mean, we encrypt data from other than keeping people from getting it. It's because it's a way to minimize noise. The more encryption you have and spreading the spectrum. So one of the things that we really want to do is to challenge the experts in the world, including especially the people that work for NSA, if any of you do, or the FSB or whatever else, to making the data available. If you can figure out there's an intelligent signal, not only will you be a hero in your secret organization, but you'll be a hero in the world. So that's why you want to make most of it available.
Well, thank you. So, a terrific lecture. Thank you very much, Pete. Don't forget our next event, The Age of M. If you fancy being immortal and being uploaded into some computer system, come and find out how that's going to be done at the Science Fact Meets Science Fiction lecture in about 6 weeks' time. Look out on the Beyond Center website for the full details. And thank you very much for coming.